Okay, let's ask what is electrical current, potential difference, electromotive force, and resistance. But before we get into that, we need to understand a fundamental physical quantity known as the charge. So what is a charge? Now we learn that atoms are made up of protons, neutrons, and electrons. Now these protons and electrons, they carry what we call charge. So one proton carries a positive amount of charge, and we have actually a value equivalent to 1.6 times 10 to the power negative 19 amount of charge. Now what is the unit of charge? It is actually the coulomb C. Okay, and one proton consists of a positive amount of 1.6 times 10 to the power negative 19 coulomb of charge. Similarly, one electron also has charge, but its charge is negative, and it's equivalent in terms of magnitude 1.6 times 10 to the power negative 19 coulomb of charge. So that is a physical quantity that we must first identify. And we understand that electrical current consists of the flow of charges. So let's look at what electrical current is. It has an SI unit known as the ampere, symbol capital A. So it's actually a measure of the amount of charge flowing through a conductor, and taken at a certain point here, we measure the amount of charge per second, amount of charge per unit time, the rate of flow of charge passing through a point in a conductor. We call that current. So the formula for current is actually, current is a symbol I equals to Q over T. Q is charge, T is time. Current I. The unit for current is ampere, unit for charge, as we mentioned earlier, coulomb, and the unit for time must be in seconds. So if the unit of charge is coulomb, the unit of time is seconds, the current will automatically be in ampere. So this is current. It is the flow of electrical charges per unit time. So having said that, we know that electrical current is the flow of charges. Effectively, it's the flow of electrons, negative charges, free electrons. So metals with free electrons are good conductors of electricity because they consist of a lot of electrons that is able to flow, to move. Insulators, on the other hand, consist of very little free electrons, so it's not a good conductor of electricity. Now there is a term known as conventional current and electron flow. Now what is this? Conventional current refers to the flow of positive charges, whereas for electron flow is essentially the flow of electrons, negative charges. Now why is there this discrepancy? The electron flow, electricity is the flow of electrons. It was only discovered that current consists of the flow of electrons somewhere in the late 19th century and the early 20th century. But before that, scientists believe that current flow is the flow of positive charges. So they have this concept that is incorrect at the time before the discovery of electrons. So because of that, all the equations, understanding laws have been built on the wrong concept that current flows with positive charges. So at that point, scientists decided that they will use the term conventional current to describe uh, the flow of current by convention. But in actual fact, it is the flow of electrons that is actually taking place. So that is the reason why we have this conventional current versus electron flow. So in all our understanding study of electricity, we use conventional current. Okay, the flow of positive charges. Now let's move on. Potential difference. Symbol capital V. Now what is potential difference? As the name suggests, it's the difference in potential. The SI unit, of course, is volts. So let's illustrate. This is a difficult concept. So let's illustrate using what we are familiar with. I have a resistor, which I have not explained, a component here. Current flows, conventional current flows from left to right. So it means that electric charges, positive charges, are flowing from the left side of this device to the right side. And there is actually this difference of potential from the left to the right. So I call this V1, V2. So potential difference V is equals to V1 minus V2. So that's the difference in potential. So what is this potential? We use something that we are familiar with. Consider a high-rise building, and we are at this point so say we have a point here. This is the second floor. Sorry, this is the third floor. We are familiar with gravitational potential. So on the third floor, a ball that is dropped possesses gravitational potential energy. Compared with the same ball that is brought to the fifth floor, this same ball would have a higher gravitational potential compared with the third floor. Similarly, at the 10th floor, the same ball would have a higher gravitational potential by virtue of its height difference. So we know that. Now, in the world of electricity, the same concept applies. There is the ball in gravitational concept drops from the point of higher gravitational potential to a point of lower gravitational potential. So from the 10th floor, you let go of the ball, it will go down to the first floor. From the third floor, you let go of the ball, it will go down to the first floor. So because of that gravitational potential energy difference, the ball will drop from a point of higher gravitational potential to a point of lower gravitational potential. Similarly, for electricity, V1 has a higher electrical potential at a higher floor. V2 has a lower electrical potential. So a positive charge will always move from a point of higher electrical potential V1 to a point of lower electrical potential V2. Just like the ball will move from a point of higher gravitational potential to a point of lower gravitational potential. So therefore we have this potential difference in terms of electricity. It's V1, the higher electrical potential, minus V2, the lower electrical potential. So there is a formula that describes this. It is potential difference equal to the work done per unit charge. So W is work done, unit for work done, joule, Q is charge, that's what we discussed earlier. Unit for charge, coulomb. V is potential difference, short form PD, unit volts. So here it says that potential difference is actually the work done in bringing a unit per unit charge, a unit of positive charge across a device. In this case, across this device, and usually we use the term resistance to describe this device. So how much work is done in bringing one unit of charge from V1 to V2? It's just like the case of the gravitational potential energy. The ball is dropped from the 10th floor to the first floor. How much is the work done in converting that ball as it moves down to the first floor into other forms of energy? So this potential difference has the same idea. Work done in bringing a unit charge from a higher potential to a lower potential. That is potential difference. Now, there is the next part on electromotive force, E. Now, what is this electromotive force? It is actually very similar to the concept of potential difference. SI unit is also volt, but EMF, E, specifically refers to the driving force of a circuit. So usually we use a cell or a battery to describe that. So in a cell or battery, the long line refers to positive terminal, the short line refers to negative terminal. And it is the driving force behind a circuit. So this is a typical electrical circuit, direct current circuit. The current will flow because there is a driving force. The driving force is the cell, and the EMF refers to the voltage of that cell. That means to say how much energy is supplied to the positive charges as it flows through the circuit across a component, a resistor. So how the current flows through this resistor is because there is a driving force E. Okay, and this E has the same formula as potential difference. So this is EMF, volts, this again is work done, joule, and this again is charge, coulomb. Now at this point, I like to draw the difference between potential difference and EMF. The work done for potential difference is to bring a unit charge across a resistor, a component. For EMF, it's not the work done to bring a unit charge across a component. It is to bring a unit charge across the whole circuit. So work done for whole circuit. This one, PD is just the work done for one device or component. So that's the difference. Both the PD and the EMF are work done per unit charge. But for PD, it is a work done per unit charge to bring the unit charge across one component. EMF is the work done per unit charge to bring that unit charge across the entire circuit. So if the entire circuit consists of only one electrical component, then the value of the EMF would be the same as the PD across that one component. Okay, so this is for EMF. If I have a circuit with two components, I call this component 1, component 2. So the potential difference over component 1, I call it V1, and that over component 2, I call it V2. The current flows from the positive terminal of the battery to the negative terminal. So this current is I. It goes through V1 and then goes through V2. So the EMF here is responsible to do work by bringing a unit charge across the whole circuit, which consists of two components. So V1 is the work done to bring a unit charge from the left side of component 1 to the right side of component 1. V2 is the same, but it's the work done in bringing a unit charge from the left side of component 2 to the right side of component 2. Okay, so this is V1 and V2, but E is responsible to bring the unit charge across the whole circuit, so it is actually V1 plus V2. Got it? So say if V1 is 3 volts, V2 is 4 volts, it means E must be 3 plus 4, 7 volts. So it is responsible to be the driving force to bring the 1 coulomb of charge across component 1 and component 2. So I hope that clarifies. Now another way to distinguish between potential difference and EMF is the description of the work done. So for EMF, the work done is from electrical to non-electrical energy, whereas for EMF it is from non-electrical to electrical energy. Why so? The current flowing is electrical energy. It carries electrical energy to overcome the resistance, the component. So when it passes through a light bulb, the energy converted is from electrical to light energy or heat energy. Whereas for EMF, it is the cell that consists of chemical potential energy or any other kinds of cell that has other forms of energy, but the net result is to convert it to electrical energy so that it can run through the circuit. Okay, finally, let's understand what resistance is. Resistance R, SI unit ohm, symbol this Greek letter omega. Now resistance basically is denoted by Ohm's law. It's defined by Ohm's law. What is Ohm's law? R is equals to V over I. R is resistance, unit ohm. V is PD or voltage, the unit volts. I is current, the unit ampere. So resistance is the ratio of the potential difference per unit current. It denotes how much, it implies how much impedance, how much resistance, how much blockage, how much opposition is acting on charge, flowing charge. So conductors like metals with free electrons offers less resistance than say rubber and insulator with a lot of resistance. It impedes the flow of charges. Another formula that we use to calculate resistance is this. This again, R is resistance. This symbol here stands for resistivity. They are not the same thing. The unit for resistivity is ohm meter. L is the length. A is the cross sectional area. So the length could be in meters or cm. The cross sectional area will correspondingly be in meter square or cm square. And of course resistivity can also take other forms, ohm, centimeter, no problem. So what is this? This formula tells us that the resistance of a conductor depends on a few things. First, the length. The longer the length, the larger the resistance this piece of uh, device provides. So L is proportional to R. Whereas for A, cross-sectional area, the larger the cross-sectional area, the smaller the resistance, because it offers a bigger passageway for current, for charges to flow. So the larger the A, the smaller the R, so it's inversely proportional. And then for rho, resistivity, it is dependent on the material. With electrical appliances, the good conductors having a lower resistivity than bad or insulating bad conductor of insulating material that offers a higher resistivity. Resistivity also changes with temperature, but generally it is the same value for the same material. So these are two ways of calculating resistance: Ohm's law and resistivity equations. So I hope I explained the difference between all these things. Thank you.